All right. Hi, everyone. These notes are going to be the Physics Journal 8, the gravity notes. So the leading question here is, what is the acceleration of a falling object? And so that would be an object that's just falling, in the air. Gravity causes all objects to fall at the same acceleration, provided we ignore air resistance on Earth. The acceleration due to gravity is 9.8 meters per second squared. So often we have this kind of misconception that says, um, you know, stuff that if it's bigger, it's going to fall faster, have a bigger acceleration due to gravity, and that's not necessarily the case. Like that's not the case, right? Everything would fall at with an acceleration of 9.8 meters per second squared, provided that there isn't air resistance. So generally, what this means is that we're just either blatantly saying we're going to ignore air resistance, or just picking objects that have a very low air resistance to the point where you can ignore it. So one of the more complicating factors that comes with starting to look at things that are going up and down is that your coordinate system becomes a little bit trickier to pick. It's not always to the right is positive, to the left is negative. When we're talking about up and down, it sometimes is advantageous to pick down to be positive. So, but like if you think about it, it makes more sense to just say that up is always positive, like that. That if there's a direction you're going to pick to be positive, it would probably be up. But there's times when downward motion makes more sense. And so my little saying here is that up is always positive unless there's only downward motion. So if you think about it, right, if an object is only going downward, it doesn't really make sense to choose down to be negative, because then your velocity is negative, your acceleration is negative, your displacement is negative. Like all of these things are negative. And if you just pick that direction to be positive, then now everything's positive and you don't have to worry about it. So anyway, that's a little saying to keep in mind when you approach these problems. So let's take a look at the example problems. So we're going to approach this in the same way that we approach the kinematic like algebraic problems 1 and 2. It says a coin is dropped into a wishing well. It hits the water 2 seconds later. How deep is the well? So we write down all the things we know. So let's see here. If we picture this, we got ourselves a little well here. We drop it from up here, right? It lands down here. And so let's think about what we know. Well, let's set this. So now that we're talking about things that are vertically, we're going to start using a y instead of an x. So this would be y naught. Oh, pen just died. This will be y naught. Instead of x naught, we're going to use y naught, and we'll call that 0. Oh, sorry, I should back up for a second. So we need to think about back to our directions, which said, right, up is always positive. Up is always positive unless there's only downward motion. So if we think about this, we have only downward motion, right? The coin only goes downwards. So we're going to call down to be the positive direction because we only have downward motion. So what that means is, right, we can set our initial position equal to 0, and then we are looking for our final position. And that's important to note that this is going to be the 0 instead of this, because as we go down, the numbers are going to get bigger and bigger and bigger because we're going in the positive direction, right? So like this is the 0 part of your tape measure. And so that's kind of the way that you can talk about that or think about that. So you have to be careful, right? Where you put y naught and y matters is determined by or where you put 0, what you call 0 is dependent on whether you're calling down up positive or up positive. It is dropped, so that tells us that v naught is equal to 0. And we know that the time is 2 seconds. And because it is falling, we know that a is equal to 9.8 meters per second squared. Note positive 9.8 because it is downward, and we just called down positive. So then, right, we got to figure out which equation we want. So it's got to have displacement in it. So only the Ringo equation and the John equation have y in it, or right displacement. And then it also has a time, so only the John equation has time and displacement in it. So I'm going to write the John equation with y's instead of x's this time. So y is equal to y naught plus v naught t half a t squared. Same equation, I just switched out the y's for, or the x's for y's. So now, right, we're looking for y, put a 0 in there, 0 times 2 plus 1 half, 8, 2 squared. Obviously that's 0 and that's 0, so you're left with just y is equal to 0.5 times by 9.8 times by 2 squared. And so 0.5 times 9.8 times 2 squared is going to give you 19.6 meters. And there you go. There's your first one. Take a look at the second one. A ball is thrown upward with a velocity of 18 meters per second. How long does it take to get to the top? Okay, so, now the ball is thrown upward. So we do have upward motion. So the very first thing to think about is, right, how do I want to set up my coordinate system? Because I have upward motion, I do want to call up positive. So that's going to be the positive direction. Right, it is thrown with a velocity of 18 meters per second. That's going to be my v naught. It's going to be positive because it's upward. I know that this thing is falling, so that's going to give it an acceleration of negative 9.8 meters per second. It is negative because it is down. We called up positive, so if up is positive, then right down is going to be negative, so hence the negative 9.8. How long does it take to get to the top? So I'm looking for t, and if we think about it, right, like what's true about the top? Well, at the top, the velocity is 0, right? So, right, the object just isn't going to be moving at the top. It's going to slow down, slow down, slow down, slow down, slow down, slow down, stop, right? So at the very top, our velocity is 0. So looking at all the stuff that we have here, that's going to be the John equation because we have a final velocity. We also have a time. Paul equation has a final velocity and a time. So we write out the Paul equation blank. Then we go ahead and put our information in it. So move that to the other side. So we're going to get, well, actually, let's move the 9.8t to the other side. So you're going to get 9.8t is equal to 18. Divide by 9.8. And so that's going to be 18. And that is going to be 1.8. All right. And last one here. A t-shirt cannon fires a t-shirt straight upwards. The t-shirt is in the air for 6.5 seconds. Before hitting the ground, again, what was the initial velocity of the t-shirt? Okay. So the t-shirt goes up. Come on now. T-shirt velocity, or t-shirt goes up, comes back down and hits the ground. So we would like to know v naught. That's what we want to know. Like what initial velocity was it thrown at? It starts and ends at the same place, so we'll just say, right, we'll call that 0. So that tells us that right? Y naught is equal to 0 and y is equal to 0, right? Its initial and final positions are the same and they're both on the ground level. So we'll call both the initial position 0 and the final position 0 because it starts and ends on the ground. It does have up and downward motion. So, right, doesn't have just downward motion. So that means that up is positive. I would recommend doing kind of what I've done here, where on each problem, I go ahead and indicate what direction I'm calling positive. So note on each of these problems, I've drawn what direction I'm calling positive. I would recommend doing the same thing just to keep things straight. Again, we're looking for the final or the initial velocity. We know that the time is 6.5 seconds. And we know that the acceleration is negative 9.8 because, again, I've chosen up to be positive. So let's see here. Anything else? I think that's it. So in looking at the information we've gotten here, that should be pretty clear that you're going to use the John equation. So, right, you got 0 is equal to 0 plus V naught 6.5 1/2 negative 9.8 6.5 squared. Whew, almost ran out of room there. So then, let's see here. 0 is equal to 6.5 V naught plus, it's going to actually end up being negative, isn't it? So let's do this. We have 0.5 times by negative 9.8 times by 6.5 squared is going to be negative 207. So add that to the other side. 207 is equal to 6.5 V naught. Divide by 6.5. And you get that V naught is equal to 31.8, 31.9. 31.9 meters per second. So there you go. Those are your answers to that. Alternatively, another way to solve it would have been to use the same trick we used up here where the final velocity is 0 and divide the time in half because it spends half the time going up and it spends the other half of the time going down. And so you could use 3.25 seconds and do the same trick we used for number 2, meaning use the Paul equation, put in 3.25 seconds, final velocity is 0, acceleration would be negative 9.8. So it'd be basically the same problem as number 2, and do it that way as well. So there's more than one way to do some of these problems. So that would be one way as well. But you'd have to kind of realize that you'd have to divide your time by 2 and remember that the velocity at the very top is 0. So that'd be another way to solve that problem. So anyway, thank you for watching. We'll see you later.